Okay, if you can take your seat, we can start the lecture. First of all, let me give you an announcement. Today, I have to quit at 10:30, so we'll do 2 hours in a row without interruption, okay? Sorry for the late announcement, but I had an issue and I cannot stay here till 11:30. So we'll do just 2 hours today. Okay, in these 2 hours, I want to start looking into the product development. This is important because this gives you an idea of the overall implementation process according to the ISO26262, and then this motivates the next part of the course. In these lectures, we will see that in order to be compliant with the standard, we must adopt specific design tools and specific validation tools to improve the quality of our system and to minimize the risk of having misbehaviors that have not been foreseen during the operation phase of our item. So it is important to understand why we need to use those techniques, and then we will start analyzing the techniques in detail. So if we look into the product development phase, we have different levels of activities that have been conceived for allowing you to address from, let's say, a top-down approach the design of an item. So we will look into the system-level aspects of our design that we have analyzed with the concept phase. Then we will decompose the system into hardware and software, and for each of these we will have specific development phases. Then when the hardware has been designed and the software has been designed, they can be integrated together. So we will have the software running on top of the custom hardware that belongs to the item. And for this, we have to do integration and integration testing. We will see the methodologies that are suggested for each of these phases. And then, as I said, this will give us a roadmap for the next lectures. But before that, let me start with an introduction. Here I have to add some other terms that we have just mentioned in the past lectures, but we haven't defined yet. So let's have a look at them, and this will also give us the possibility to introduce some concepts related to the evolution of faults during time. Maybe some of these terms we already have introduced them, but let me recap them again. So the issue we want to deal with is the failure. We know that something is going to stop working properly in our item, and so we have to be able to cope with that. The first thing that we have to recognize is that the malfunctioning will result in a failure. This means that our item will terminate the ability to deliver the expected service. The failure is provoked by a fault. So the physical component that gets broken due to aging, due to incorrect assembly, due to an accident that we haven't recognized. Think about when you have sensors on the bumpers of your car. You have the car parked somewhere, and somebody else, when you are not there, makes an exit from the parking lot and crash into your bumpers. You don't recognize that because you are not there, but it may happen that the crash breaks the sensor that is used for your Q-assist device, just as an example. So these are all cases of possible faults. Then we said that when our system is affected by a failure resulting from a fault, and so it is not able to provide the expected service, whenever we enter in an operational situation that can be hazardous, if the failure happens when we are asking the service out of the item and the item is not able to deliver this due to the fault, we have to be able to provide the system, the item, the capability of entering into a safe state. This means that even if the item is not behaving as it is expected to be, it doesn't produce any harm to the user. And this is obtained by letting the item entering into the safe state. The hazard is the potential source of harm. That is the scenario in which we can ask the service from the item and the item is not able to provide it. And then the fault can be either manifest, this means that you are perceiving that the fault is in the system and it is producing a misbehavior that results in a failure, or the fault can be latent. This means that you have a broken component, the broken component sooner or later will produce a failure, but until you get access to the function provided by the item requesting the service, so until you start using the item, you can't see that the failure is there. And this is the example of latent fault. Let me explain this through an example. Let's have a look at the timeline that I presented here that gives you a rough idea of the evolution over time of the different situations that could happen. So this axis here is the time. So let's imagine that at any given time there is a component in your system that stops working. So as an example, let's imagine that you have an item that is made out of an electronic board. In this electronic board we have a component like let's say a resistor that is needed to provide a bias voltage to the input of the microcontroller. So let's imagine that that resistor broke. So the resistor is no longer able to work properly. That is the fault. Whatever is the physical source that produced the loss of service in the resistor, we just know that the resistor is no longer working properly. That moment in time is the time when the fault happens. Then let's imagine that we are not using the item. Let's imagine that the item is the item needed for braking. Okay, so we are driving. We have the braking system that is affected by a fault because we have a resistor that is no longer working. But until we hit the brake pedal, we are not able to recognize that the fault is there because we are not asking for the service provided by the faulty item. That is, the item is faulty, but we don't know yet that something is not going wrong, is not going as expected, because we haven't yet started using the function provided by the item. We haven't yet hit the brake pedal. So the time that spans from the occurrence of the fault till the manifestation of the fault is an amount of time during which the fault is latent. This means that the item is affected, so it is not working properly, but we haven't yet had the chance of recognizing that the fault is there because we haven't used yet that item. Okay? So during this period of time, the fault remains latent. Then we could have two different scenarios. We could have the fault that remains latent for a while, and then, thanks to the mechanism that we have introduced in the item to prevent malfunctioning due to fault, we are able to detect that the item is not working properly. So think about the example that we analyzed last time about the QA. We have seen that as one of the functional safety concepts, that the item must be provided with self-testing capability. And in case the test procedure recognizes that the item is not working properly, we must enter the safe state. The safe state is disable the item and inform the driver. Okay? You may remember this. Well, the mechanism that provides the capability of recognizing that something is not working properly could work during this amount of time since the occurrence of the fault. And then after a certain amount of time, we could end up saying the item is faulty. I am entering the safe state. So this is the time when the fault is detected, okay? And it is this amount of time here. Then if we are able to detect the occurrence of a fault, so we detect that something is not working correctly, the resistor is not providing the correct bias, and so the microcontroller is not able to perform the proper action, we must react to the fault before the fault becomes a failure. So what is important is that first we recognize that something is not working properly, and then we put at work some corrective actions that are intended for preventing the hazard. So this means that once the fault has been discovered, the item has to react. This reaction time is the time that the item takes to enter the safe state. Let's imagine that if we recognize that the braking system is not working properly, we reduce the vehicle speed to 0, okay, by working through the powertrain. So we are not able to brake the car, but we can reduce the speed of the car by reducing the request for acceleration on the engine, and we can leverage the engine brake so that we can stop the car. This will take some time, and this time is the time that spans from the detection of the fault and the time when we enter the safe state. So you have to imagine that our mechatronic system hasn't the capability of reacting in 0 time. Whichever action we have to take, it requires some time. So this is the fault reaction time. While the time that spans from the occurrence of the fault till the detection of the fault is the fault detection interval, okay? Then, once the fault has been detected, it could produce a failure. So it could happen that the fault manifests itself because since we detected through the self-testing mechanism of our item that there is a fault, the driver asks to brake the car. Clearly, this could happen after the detection and before the entering the safe state. So in this period of time, the item is not providing the expected service. And in this time, we could have the failure that becomes evident. This is clearly a problem, because if we think about the braking system, the braking item, here is where we recognize that the item is broken. Here is T-safe, when we are able to provide a degraded service that is still safe for the driver. And this is a period during which the driver could be exposed to the hazard, because we recognize that the system is not working properly due to the fault happening here. We haven't yet reconfigured the system, and so we are not able to provide a safe operation mode. We are in the transition between the not working situation into the safely working situation. So if the driver asks to brake in this amount of time, we could have problems. because the item is not yet able to provide the saved service, and it is not able to provide the expected service. Okay? This is called the emergency operation interval. That is the time that spans since the occurrence of the fault till the entering in the safe state. During this period of time, the hazard could produce an harm to the people in the vehicle or around the vehicle, because the item is faulty, it is not producing the expected service if asked from the driver or any other people around the vehicle, and we are not yet into the safe state. Then, what could happen is that we have the fault, maybe we are not able to detect it, so the fault could manifest itself. As we haven't been able to detect the fault, we cannot enter into the safe state, and so eventually we have the hazard. So let's imagine that we stay into the brake system example. Here the resistor broke. Here the driver asks to brake the car. This is not happening, so the car continues to perform operations that are not those ones that the driver wants to have. So we are, if you remember the state diagram that we have seen, we have the incorrectly working operation in use, then we enter in the hazardous situation, we are not able to guarantee the intention of the driver, and eventually we have the hazard, okay? So, if the fault happens, we do not detect it, then the fault becomes a failure. We cannot enter in the safe state because we haven't detected it, then eventually we will have the hazard, okay? The amount of time that spans from the happening of the fault till the hazard is the fault-tolerant time interval. So this is the maximum amount of time we have available to put at work some mechanism for avoiding reaching the hazardous state, okay? All these times, as we will see later on, are part of our design. So when we specify how we want to implement the functional safety concept, we have to state how we will perform the detection, how we will transition to the safe state, how long does it take to perform the detection, how long does it take to react to the detection of a fault before entering the safe state, and we have to specify which is the maximum fault-tolerant time interval. So all of these are specifications that we have to give. But we will see this at the due time. Okay, so the slides that I am presenting here are just the explanation of the concept that I gave you. So it is not worth to spend time again here. And this gives you the evolution of the system in the two possible scenarios. Let me recap again this. So here is when the fault happens. So the fault is latent because it is affecting the item, but nobody asked the service from the item. Then, due to the mechanism that we have in the system, the item is able to detect that the fault is there. So we enter a period of time during which the item is placing into work some reactive actions to enter into the safe state. So clearly here we are not able to provide any service, neither the degraded one nor the expected one. And then in this period of transition from detection to safe, we could have the fault happening that becomes a failure. So, thanks to the fact that we detected the fault, after a certain amount of time, we enter in the safe state. This means that the item is not able to provide the expected functionality. Instead, it is providing another one. But in this case, the provided functionality is safe. Okay? So even if the fault is there, we will not kill anybody. Here, it is the opposite case. So the fault is there, we are not able to detect it, sooner or later it becomes a failure, and then, if not mitigated, it will become an hazard. So here, somebody is at risk, okay? Now, what we want to do with the hazard analysis and risk assessment is to understand how great is the risk for a person when using our item. Based on that, we can decide which is the criticality of our system, and then we can decide whether it is the case to put at work some techniques to guarantee the capability for the item to enter in the safe state, or if we can accept that the risk associated with the item to produce an hazard is so remote that we can do nothing. So once we decide that we have to do something, so we have to provide some functional safety concept, we have to specify the safety goal, the functional safety concept, and then we have to implement it. This is part of the implementation phase that is divided into, let me say, levels. There is a first level that is the system level that can be clearly outlined here. So here we analyze the outcome of the hazard analysis and risk assessment, and we decide how to implement the functional safety concept. So here we take decisions. Do we do our implementation as a combination of hardware and software? Do we do only hardware? Do we do only software? Which are the techniques that we want to use in hardware, in software, and both? These are decisions that we have to take at this level. And then we can go ahead with the product development, bringing together the development of the hardware and the software. I mean that we have to bring this together because even if they appear as two separate actions here, there is an interaction between the two. Once we design the hardware, if we recognize that we are not able to meet the requirement that has been specified at the system level, we may decide that we want to add some software, some more software to cope with some faults that we haven't considered at the system level. And this will have an impact on the software side. Similarly, when developing the software, if we recognize that we are not able to satisfy the timing requirements that somebody has specified at the system level, then most likely we have to do something in the hardware. So even if hardware and software are developed independently, there is a correlation between the two that is happening well before the integration and testing. Let me now start analyzing the different phases that are foreseen for the system level design. The system level design is started with the specification of the technical safety requirement. So here we are adding a bit more detail in the design of our item. Out of the concept phase, we have the safety goal. Then, from the safety goal, we derived the functional safety concept. Here, we transform the functional safety concept that are still abstract into something more detailed. And this is the specification of the technical safety requirement. So here, we give a refinement of the functional safety concept, and we start considering how to actually implement this into hardware, in software, or the combination of the two. Another element that is very important here, that we haven't found yet, is the verification step. This is relevant for all the product development. From now on, our different phases of the development flow will always have a two-step approach. The first step is let's specify what we want to do. Then do it. The second phase is check whether what we did is consistent with what we specified. This is a two-step approach. First, we declare what we want to do, then we do it, and then we verify whether what we did is consistent with what we specified. This is very important. This is very important because through these verification gates, we have ways for inspecting the result of our design activity to be sure that we did exactly what we were expecting to do. And so that we move forward with the next phases, having confidence that we did the right job. This is very important. Remember that here, if we do mistakes, somebody gets hurted. So we want to avoid that this is happening. The process is very complex. So the only possible thing is to decompose the process in multiple design steps. Each step has a gate. You can proceed to the next step only if you successfully did all the operation envisioned for the current step. Then the standard requires you to specify a lot of things here. You have to specify how you intend to detect the fault. Then you have to consider both the faults that could happen inside the item or the faults that could happen in the item interacting with our item. So that's why when we do the item definition, we look into the function provided and the function required. So let's imagine that our item requires to receive through the vehicle network certain information. What happens if that information is not provided? What do we do? What do we do to understand that the item with whom we have to interact is not able to provide me the expected information? I must be able to recognize that. Okay? And this is something that must be specified here. Then I have to specify which are the measures, which are the mechanisms that I want to use to transition into the safe state and to maintain the safe state. This mechanism shall specify the transition to the safe state and all the timing associated with this transition. So this means that here we are defining the architecture of our system. We are specifying which are the implementations that we want to do for the functional safety concepts, including the timing aspects. Here we haven't yet started designing. We are not yet started implementing anything. So we haven't started the schematic editor to lay out the PCB of our board. We haven't yet started writing code. Here we are still thinking about what we want to do. And we have to refine this specification, providing all this information. Then, once the specification is done, we can start the design. And the design, as I said, is made of two steps. We do the design based on the assumption that, based on the specification that we provided, and then we check whether the design is consistent with the specification. We are not going into much detail here. Let me just say that this is where we allocate to hardware and software the specification that we gave when defining the technical functional safety concept. As an example, one of the faults that we have considered in our analysis, think about the QA or the CTA, is the microprocessor is broken, is not able to execute software. Okay? Then we said that out of that failure, we could have an hazard. Let's say we are not able to inform the driver of an incoming vehicle, or we are not able to close the speed loop to keep the safe distance from the preceding vehicle. Okay? These are examples of manifestation of the fault. Then one of the safety goals that we specified is that we have to be able to provide the service correctly to the driver. And one of the functional safety concepts was we have to implement a self-test mechanism and inform the driver if something is not working properly. Then how we do that? For example, if we want to cope with the fault that prevents the microprocessor of running a software, we could have monitoring features that are inserted in our system that are responsible for checking whether the microprocessor is running software or not. We already have seen this when we spoke about the Toyota case, and this is the typical use case for a watchdog. We will go in more details about this later on, so for the moment, let me just take this as an example. Once we completed the concept phase, we enter in the implementation phase. So first, we have to specify how we want to implement each functional safety concept. And then we have to assign this specification to hardware and to software. One element that I want to stress with you is the verification aspect. The standard says that you have to verify whether your design activity is consistent with the specification. But it is also going much more ahead. It is also giving you recommendations about how this verification must be done. If you have the chance of access to the standard, you will see that there are plenty of tables like this one. What's the meaning of the table? Well, this table is the recommendation for the specific step in the design process that you have to follow in order to be compliant with the standard. Normally, the table contains a method column. This lists a number of different methods that are suggested or mandatory for addressing that specific step of the design flow. So, for example, here we are dealing with the verification of the system design. This means that we are looking into the techniques that the standard suggests for verifying whether your system design is consistent with the technical functional safety concepts and with the safety goal that we have specified in the previous phases. We will see that we will have something similar for other steps of the design phase. We will see this in a minute. Then, the other columns that we have here comes under the ASIL label. This means that depending on the result of the hazard analysis and risk assessment, you will have different recommendations. So you will always find a column for ASIL A, one for B, one for C, and one for D. Then here you have the different rows that compose this table. In the row, you can see the description of a method, like, for example, simulation. Simulation is one of the methods suggested for verifying the correct design of the functional safety concepts and the safety goal. Or you can have system prototyping and vehicle tests, you can have system design analysis, you can have system design inspection, system design walkthrough. Those are all techniques that are described in the literature that can be used for going through the documents that you provided out of the specification phase, out of the design phase, to check whether what you design is consistent with what you specified. You can see numbers here, 1A, 1B, 2A, 2B, 3. So the number 1, 2, 3 is a sequence number for the method. Okay. If the standard says that you have 3 different approaches for different methods for performing that step, this means that you have to apply all of them. So you have to take one method labeled 1, one method labeled 2, and one method labeled 3. Then you can have multiple options for each of these sequence number. As an example, we can see that the method 1 can be either 1A, system design inspection, or 1B, system design walkthrough. For the 2, you can use either simulation or system prototyping and vehicle tests. For the 3, only system design analysis is provided. So this means that when you define your design process, you have to say, well, in order to be compliant with the standard, the verification phase foreseen during the system design will be made of system design walkthrough and simulation and system design analysis. Okay? You have to pick one of them. And if the standard says you need to use 3 verification techniques, you must use each of them. Okay? Then here you can see a matrix where you have plus, 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 O. Okay? What does it mean? Well, O stands for optional. So you can use it or not. It is up to your choice. When you see plus, it means that the method is recommended. So you can decide what to do, but it is best if you decide to use that method. When you see plus, plus, well, you are strongly recommended to use that method. This is to say, you must use that method. Can you explain me what is so funny that you are laughing since at least half an hour? You and your colleagues beside you that is looking out the table and it is smiling. No, I'm just curious because I see you so funny, so I would like you to share this fun with the rest of the class. Can you tell me something? Do you have a joke that you want to share with the class? Please. Okay, so let me give you an example. Let's imagine that we are designing an item that is ASIL A. Okay? Once we reach this point of the verification, we have to take, for example, system design inspection. This is suggested. Or better if we take system design walkthrough. This is strongly suggested. So let's say that we take system design walkthrough. Then we take, it is the same, either simulation or system prototyping and vehicle test. And eventually, we have to take a system design analysis. Here, we have to refer to another table to have more details, but let's say that we have to take system design analysis. Conversely, if we have to design an ASIL D, well, you can see here that system design inspection is highly recommended, while system design walkthrough is optional. So when deciding what to do here, you will take system design inspection. Then, as far as the point 2 is considered, you can take either simulation or system prototyping and vehicle test. They are the same. They are both strongly recommended. And then we have to see for this table what is suggested for system design analysis. So here you can start appreciating the fact that designing according to ISO26262 could be very expensive because you have to put at work a number of steps that are compulsory, so you cannot avoid them. The best practice of the automotive industry recognizes that after the system design, there must be a verification gate. This verification gate is considered done in the proper manner only if you adopt the techniques that are listed in this table according to the prescription given by the standard based on the different ASIL that you have. So this has a huge impact on the automotive industry. Well, first of all, this is not science fiction. These are all techniques that are in use in the automotive industry since a lot of time. But maybe not all the companies that are willing to provide electronic system for automotive are using all of this. So if you want to stay in the business, you have to update your process. And this could be expensive. Think about small and medium enterprises that never used simulation. Simulation tools are expensive. Here you are used to use Simulink or Model Sim or whatever other simulator that you have been exposed to during your training period. So you take this for granted. But you have to remember that these tools are very expensive. So you can install Simulink for free on your machine. If you are in the business and you want to do this in the legal way, you have to buy licenses. This means that you have to spend at least 20K euro for each PC of your lab. So this is very expensive. And this is just one example. In our class, we will use Embedded Coder. Embedded Coder is the tool that generates software starting from Simulink. Well, if you want to buy a commercial license of that, I think it is close to 15K euros for one site, okay? So adopting this standard could be very expensive for a company. But this is something that must be done. Otherwise, you will not be in the business anymore. So you have to put in the proper perspective what I'm saying. Using the process is important, but it is hard. Then, let's imagine that we did the system design. Let's imagine that we did the verification successfully. Then we can move forward towards the implementation. And here we have the hardware level design and the software level design. We'll go quicker on the hardware and we'll stay more on the software. So, when we arrive at this point, here is where we start opening the schematic editor and we start designing our item, so the hardware part of our item. Here, the standard prescribes a pretty strong and regulated process, obviously. We have an initiation phase, then we have the specification of the hardware safety requirements, we have the hardware design, we have then we have the assessment to validate that what we designed is consistent with what we specified. As we want to adopt a top-down approach, the hardware design will be decomposed into design of multiple hardware components. So we have to define the constraints for for our architecture. Then we have to, once the design is done, we have to assess the criteria for the probability of violating the safety goals. Then we have to do hardware integration and testing. This means that we have to bring together all the different hardware elements to assemble the resulting hardware of our item. And then we have to check the safety requirements for the hardware-software interface. So it is a strong process. We will not go into the detail of this. Let me just say that we will support a top-down approach. So we specify the architecture of the hardware, we decompose this into components, we design each component, then we integrate the components and we ship our hardware after having verified that the design that we did is consistent with what we specified. This is the global picture. Well, again, here we have some recommendations. For example, if we have to perform the verification of hardware safety requirements, the standard suggests these techniques, either walkthrough or inspection and simulation. And again, you can see here the table that we analyzed before. We have the methods and we have the ASIL, and then we have to pick one of these techniques when we have an option, and we have to apply them based on what the standard suggests. Again, you may want, this is not science fiction, you may wonder why we have this distribution of plus, 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 and O. Well, this is again related to the best practice of the automotive industry. You have to imagine that the standard ISO26262 is the result of several years of discussion where different experts coming from the automotive business grouped together and analyzed the best practice, so what they are doing in their respective companies. And then after comparison, discussion, analysis, they distilled these tables. So this is what the automotive industry globally recognizes as the best way for doing the activities. Okay. Then one of the steps that we have to go through is the hardware design. So far we have spent tons of papers or Excel file to specify, but now eventually we have to design something. Here, the design must be inspired to a number of principles. For example, you must use design guidelines and standards. So your company must provide a book where all the design guidelines are specified. You cannot use a PCB that is larger than this area. You must use components out of this recommended part list. Each component must be placed on the schematic according to a certain spacing. The soldering process must be done according to these techniques, and so on and so forth. So you have a number of elements to be conveyed into these design guidelines, and then you must adopt them. Then you need to use a hierarchical design, modularization, robust design, and as you can see here, the more you move closer to the D, the more stringent the recommendations of the standard becomes. So if ASIL-A basically mandates only the adoption of design guidelines and standards, while the other techniques are suggested but are not strongly suggested, we can see that when we go to the ASIL-C and ASIL-D, practically all of them are mandatory. This is because that ASIL D is much more relevant from the safety point of view than an ASIL A, and so we must put the proper care in our design activities. This distribution of the recommendations also gives you another way for reading the standard. It is clear that using all these techniques is expensive. So where do we have to spend the money? Where is spending justified? Only where a possible fault that is not detected produces an high risk for persons. So adopting all of these techniques is justified for an ASIL D, because if something goes wrong there, somebody will be dying. For an ASIL A, the risk is much lower, so it could not be justified to spend all the money that this requires just for designing something that our hazard analysis and risk assessment deemed as not very risky. Okay? It is clear that we want to achieve the maximum safety that is reasonable for our user. But over-designing is not the solution, because otherwise the result of the design process will be too expensive to be appealing for the customer. So we have to try to find the good trade-off between the amount of technique that we deploy to provide the safety and the cost of the item that we are producing. So this trade-off is guided by the ASIL. The higher the ASIL, the more we have to spend. The lower the ASIL, the less we can spend. Okay? Then, to clarify one aspect related to the spending, I reported this slide. For ASIL C and D, the standard says that you should use well-trusted hardware element. This means that when you are designing ASIL C and D, you cannot use whichever microprocessor is on the market, for example. Otherwise, it will be very difficult or even impossible to be able to provide evidence that your microprocessor is providing you a risk that is acceptable. If you want to be successful in designing hardware for ASIL C and D, you have to go on the market and you have to buy specific components that have been designed for being ASIL C and D compliant. What does it mean? The manufacturer of that specific microprocessor that is ASIL D compliant put at work a number of techniques that guarantees you that no matter what is happening inside the microprocessor, you will always know whether the microprocessor is working correctly or not. So you don't have to take care about understanding whether the microprocessor is faulty. This is done automatically for you. And this can be very complex. One technique that is used, for example, is to duplicate the computing cores. So you have one software that is running concurrently on two independent cores. They do the same operation, and then the hardware contains some modules, specific hardware modules that are called redundancy checker, that compares the output produced by the two cores, and if they are different, the output is not delivered to the user. Instead, an error indication is delivered to the user. So the microprocessor is able to understand autonomously whether something is going wrong. But then, in order to cope with possible design flaws, we just don't take two cores, do copy-paste, and put them in parallel to identically copy on the silicon. For example, one core is laid out with a certain geometry, the other one is laid out with an orthogonal geometry. This means that one core can be stitched like a rectangle that is very tall and very thin. The other one is rotated by 90 degrees. So in this way, it is not possible that we have a transistor that has been designed in one core that is exactly faulty also in the other core. So this is a very complex job to be done by a silicon vendor. And so, guess what? They will charge you more for that microprocessor. If you have a certain instruction set and you don't care about safety, you can get the microprocessor for 1 cent. If you want to have the same instruction set that is ASIL-D compatible, you can spend 10 euros, okay? You have to pay more, but this extra expense is justified if you have an ASIL-D or ASIL-C application and you want to avoid unnecessary risk. Other example, let's imagine that you have to design an item that contains a sensor. Whatever it is, it contains a sensor. If the application, the item is ASIL-A on B, it is worth having a technique to understand whether the sensor is working or not. But probably it is a waste of money to duplicate the sensor, because if the sensor is not working, the item is not providing the functionality, but the functionality is not critical. So the duplication is not justified. Conversely, if we have an ASIL-C and ASIL-D application and we have sensors there, probably duplicating the sensor is very important, because we must be sure that either we are able to sense always the correct information, or we are able to understand that the sensor is not working properly with the shortest fault reaction time as possible. Okay, these are the type of technique of reasoning that you have to put at work when addressing hardware design with ISO26262. We will do some exercises to better catch this concept. Then, once your hardware design is done, you have to do an analysis. Well, this analysis basically is based on certain metrics. Those metrics are the one that could provide you a good indication of the residual risk associated with the usage of that hardware. And these are, for example, single point faults. That is the amount of faults that are detected by the mechanism that you placed in the hardware. The residual fault metric, that is the amount of faults that could impair the normal operation of the item that your mechanism have not been able to detect. And then if the dual point fault metric, that is the faults, the portion of faults that could lead to the violation of the safety goal due to the combination of two independent faults. So we have, let's say, a number of metrics that we have to evaluate for our design. There are techniques for doing that. And then let me go to the conclusion. We have some prescription. So the standard gives which are the metrics that have to be used, and then gives you the target that we have to fulfill. So if we have, for example, an ASIL-D design, for a given metric, we must reach this value. For an ASIL-C, we have to reach this value. For an ASIL B, we have to reach this metric. So what is relevant here is not knowing the exact meaning of the single metric. For the moment, what is important is to understand that our standard gives us target to be satisfied by our design according to a set of predefined metrics that are ways for evaluating our design. So what the designer has to do, when the hardware design is completed, the designer has to analyze the design that he or she produced, computing the metric, and then checking whether the metric provides the expected target for the different ASIL that we have obtained out of the hazard analysis and risk assessment. Okay? So we do the design, then we compute our metrics, we check whether the metric is satisfied, whether the target is satisfied or not. Then we have a process that is this one. So what we have to do here? So clearly, we have to check whether we meet the target. If we meet the target, we are happy. The design is good. We can move on. If the target is not met, well, we try to add some additional mechanism to cope with the portion of faults that the current design is not able to deal with. Then we check again. Are we on target? If yes, we are happy. We have done our job. If not, we have to redesign. So here we see again the application of the concept that I described before. This is the validation gate. If our design, according to the metrics, is able to meet the required target for the given ASIL, we can move forward. If not, we have to reiterate until we are able to meet the gate. Okay? Then, today is important that you understand the process. Then the details, we will have exercises to understand the details. For the moment, it's important that you get the concept. We do an activity based on specification. We verify whether we meet the specification. If yes, we can proceed. If no, we can stay. We have to redesign. Okay? Then, which are the techniques that are suggested? Well, there are a number of them that are based, where is it? Okay, we have to do techniques like, for example, failure mode effect analysis to understand whether our design is able to meet the requirements or not. We will do an exercise about this later on. Then, let me move forward, because this is what I want to target, that is the software level. Here, we will find material that will guide us in the rest of the course. So here, we will find the justification for the adoption of the model-based design approach that will address most likely starting from the next week, probably next Friday. No, sorry, next Friday is Easter. So we still have a lecture next week on Wednesday. We will do exercise that, and then we will meet after Easter. So, what's the purpose of product development software level? Well, it's clear. Here we have to address the implementation of the element of our architecture that has been assigned to software. So again, we will do an initiation phase where we declare which are the tools that we want to use. Then we have to specify the software safety requirements, so how we can implement in software the technical functional safety concept. Then we do software architecture design. We do software unit design and implementation. We do software unit testing, software integration and testing, and eventual verification of software safety requirements. Why I am stressing this part? This is because it is very likely that you will end up in a company touching this part of the standard. It is very often that a newly hired engineer is involved in the unit testing or integration testing. This is because there is where you can understand the detail of the item that the company is designing. It is a job that forces you to understand clearly what the company is producing. So don't get surprised when they offer you a job in the unit testing or integration testing department. It is the normal way of entering in a company that produces something, because when you do testing, you have to understand precisely what the item is doing. Then later on, you can be involved in the software unit design and eventually software architecture design when you have a better experience on the job. As you can see from this description, the design process is again top-down. You design the architecture, you decompose the architecture in components, you implement each component, you test each component, then you assemble them, you test the assembly of the components, and then you verify whether you meet the software safety requirements. So again, at the end of this process, there is the verification gate. If we pass it, we can move forward. Otherwise, we have to redesign. So the initiation is again the place where we state which are the tools that we want to use in our design process. So here we have to define which are the methods that we want to use, which are the guidelines that we want to follow, which are the tools that we will adopt, and so on and so forth. So here we set the context. I will do the design using Simulink, embedded coder. I will do validation using Polyspace, and so on and so forth. So here you just say what are the tools and the methods that you want to adopt. Examples. These are suggested from the standard. You have to enforce low complexity. You will have to use language subsets. You will have to enforce strong typing, and so on and so forth. So all of these are suggestions that are provided for guiding you in the definition of the environment that you want to adopt. Here you can recognize something that we have seen when we spoke about the unintended acceleration case. You may remember that when analyzing the Toyota software, the investigator recognized that there were implicit typecasting, there were some portion of the code too complex, that there was too free use of programming language, and so on and so forth. Well, here you can see countermeasures to that. you can see that you need to use, for example, a language subset. You cannot use dynamic memory allocation, for example. You cannot use, you have to use strong data typing, so you cannot do implicit cast conversions, and so on and so forth. So here you have to say which are the instruments that you are going to use in your design. Then once you completed this phase, you can start specifying the software safety requirements. Then you have to specify how your software will interact with the hardware. So this HSI stands for hardware software interface. So you have to specify which portion of the hardware you're going to use to provide safety. Think about the watchdog. The watchdog is an hardware device provided inside or alongside a microprocessor. Who is going to program that? Who is going to use it? Who is going to trigger the watchdog to start counting, and who is going to react on the expiration of the watchdog? These are all elements that you have to specify here. Then, when specifying your software safety requirements, you have to define which of your software will be responsible for enabling the system to achieve and maintain safe state. So safe state is a goal. We want to enter the safe state. How we do that? Do we do this with software? Okay, which function is responsible for triggering the reconfiguration of the system so that we enter in the safe state? Then, do we do fault detection in software? Let's say we recognize that we have to deal with errors in the communication channel. How we do that? Do we have a function that is able to take, to keep track of how long is the last time when we received something on the CAN network, for example? Let's say we have sensors. Do we do some range check on the provided values from the sensor to verify whether the sensor provided something, and if the value provided is within the working range of the sensor? So these are all checks that you can do in your software to deal with possible failures that could happen due to faults affecting the internal of the system or the elements that interact with the system. All of these are techniques that you have to mechanisms that you have to specify here. Then you will have, once the fault is detected, to notify to somebody else the detection of the fault, so that the function that triggers the reconfiguration for entering the safe state is activated. And this has to be done here. Then, once we completed the specification, we can define the architecture. So we can have a rough, let's say, conception of how many functions or how many objects or how many modules will compose our software, how they interact. This is a complex part. Remember that here we will not deal with programming, starting opening the editor and typing diesis include standard IO.h. This is not the case. This software will be complex. You will have components, like, for example, the software component for communicating over the network, the software component for interacting with radar and retrieve the distance after a very complex chain of filtering operation is performed. Then you will have the software component that contains, for example, the intelligence of your item that, based on the information received by the different sensors, decides what to do. Maybe it is the case that not all the software that will be on your item is designed by you. For example, you can go on the market and take from experts some specific piece of software that are implementing very specific functionality that you recognize is better to buy on the market rather than start implementing on your own. Okay? So the software that you are deploying is very complex. It is made of multiple components that should be interacting in some way. So either you have a clear architecture of all these components and a clear idea of the interaction of this, or otherwise you will never be able to end up with the design of this software. So for this, you must define an architecture. Here you need to have some people more skilled than the newly graduated engineer that has a system-level view on the software, that is able to define the architecture. Then the architecture will be composed of multiple software components. Some of them will be buy, some of them will be make. For the ones that are make, there will be a further decomposition in functions, and then there will be work for you. So you will start coding the different functions. And once this is done, there will be the verification of the software architecture. Again, the standard provides you some guidelines. For example, you must use either informal, semi-formal, or formal notation for specifying the architecture. As we will see, one of the standards that is becoming heavily used in industry is AUTOSAR. AUTOSAR is, as we will see, a way for describing software architecture. It is even more than that, but for what is relevant for us, that is a way for describing software architecture. So we will have a glimpse on that technique. Then, which are the principles of the software design, software architecture design? Again, they are suggested by the standard, so hierarchical structure, restricted size of software components, restricted size of interfaces, restricted use of interrupts. So the designer of the architecture is not free to choose whatever it has in mind. There must be some activities guided by principles as suggested by the standard according to the different ASIL level. Okay? Then the standard also suggests you techniques to deal with fault detection. Remember what we have to do. First, we have to detect that the error is there, and then we have to reconfigure to avoid that the error becomes, the default becomes a failure. Okay? So the techniques that are suggested are for the detection, range check on the input and output data. We will do this in our exercises. Remember that here everything is specified. So you have a sensor, for example, that is operational in the range from 1 meter to 20 meters. The first thing that you have to do when you read the distance out of that sensor is to check whether the value is between the smallest value that can be produced and the highest value that can be produced. If not, there is something wrong. This is very trivial, but it is very effective. So whatever is the input that you are getting, check whether it is in the expected range. Before committing an output, so before issuing a command to an actuator, check whether the application logic produces a command that is between that is inside the specification of the output. You have to produce a current from 10 millivolts, a voltage from 10 millivolt to 25 millivolt. Is your software providing an output in that range or below or above that range? If this is the case, that is an indication that something went wrong. Then you can be asked to enforce plausibility checks. Let's say when the input A is 25 milliamp, input B must be 60 degrees. If this is not happening, that the incoming data are not consistent, they are not plausible. So we must react to that. It is an indication that something is wrong. And then we can have advanced features like detection of data errors. Let's say we could have some parity bit or other techniques based on the duplication of critical variables. Then we have to check whether there was a parity error or a misalignment of the duplicated variables. These are all techniques that you can use for detect the error. We can resort to external monitoring facility. Let's say we have a processor that is working alongside the main processor. It is responsible for checking whether everything is behaving properly. And then we can have, for example, control flow monitoring. There are techniques to check whether the software is executing consistently with the structure of the source code that somebody has specified. I'm going very quickly here because I want to give you the broad picture. Then we will go in detail through examples. Okay? So this is a kind of summary of what we will see later on. Then what about error handling? Well, here we will have techniques like graceful degradation. We recognize that we are not able to have the ABS working on the 4 wheels independently because there is a failure somewhere. Well, we enter degraded mode. We will apply the same correction on both the tires that are on the same axle. So either we work on both the 2 front tires or the back tires. We can have independent parallel redundancy. This means that if we have a function that is so critical that must always produce the correct result, no matter if there are faults, we can decide to execute concurrently multiple instances of that function and then vote among the output produced. Again, don't be scared about these concepts. We will analyze them with examples. For the moment, it's important to get the big picture. Then we have to do verification. We specified, we designed, now we verify. The standard is pretty strong on what we have to verify. The verification will be done using a number of techniques like walkthrough of the design. So we look into the specification document and we check each part of the design to verify whether the specification is satisfied or not. We will, and this is similar to the inspection of the design. We will do simulation. So we have our code, we run our code in a representative environment, and then we will stimulate our code with workload similar to what could happen in the system during normal operations, during faulty operations, to check whether the system reacts correctly or not. Again, we have a number of methods that are needed for checking the consistency of our specification with the goals. Then, once we are happy with what we have specified, we can eventually design. So here we have the composite the architecture in modules. Now we start writing code. So how we do that? We have a number of possibilities. We can use C code, we can use formal notation, we can use informal notation. There are a number of possibilities. We will learn how to design our units starting from Simulink models. So we will not write C code. We specify the functionality that each unit of our software has to implement through a Simulink subsystem. We will simulate the subsystem to verify whether it is consistent with what we want to achieve, and then we will produce code automatically to be deployed on our hardware. This is a way for obtaining automatically the principles that the ISO suggests as good design principles. So we will have, for example, no dynamic objects or variable. We will have all the variable properly initialized. We will not have multiple use of variable names. We will have a limited use of pointers, no implicit type conversions, no hidden data flow and control flow, no recursion, no unconditional jumps, and so on and so forth. All of these are principles that, according to the investigation of millions of lines of code, can be declared as the good design principle to follow when writing code for automotive. If you do not adopt an approach based on models, where you specify the model using an abstract language, like Simulink, and then you resort on a tool that automatically generates the C code starting from the model, you will have to write the code on your own. And while writing the code, you must enforce these techniques. This can be quite complex for a designer, because you have to have a clear understanding of the design guidelines, of the design principle, and you must adopt them. Well, this can be not trivial at all. For example, one of the design guidelines may require you to adopt a specific naming convention. So this means that the names of each object inside your design must follow certain rules. So the variable must start with an uppercase letter. The first 3 letters of the label must be equal to the name of the function that you are designing. Then there must be another set of characters that can be up to 10 characters specifying the meaning of the object. Then you need to have a trailer on the name with a certain set of characters that gives you the visibility of the object. So it can be very complex. If you have to do this by hand, it is very likely the chance that you miss something. It is very likely the chance that you do mistakes. Okay? So it's better to use an automatic approach, because the tool that somebody wrote for you and checked for you does all these stupid tasks automatically. You don't have to care about that. Then, once you completed the design of each unit, you must validate the correct operation of the unit. This means that you have to do checking, you have to do verification, you have to do analysis. So all of these steps are required by the standard. So you have to provide evidence that you did the checks. But if the checks are done on code manually written, it can be very, very difficult to do this. So better if we have the software produced automatically, because we will be able to do all these checks automatically, and your task will be much more simpler. I don't want to hurt those of you that are belonging to computer engineering, but you have to remember that writing the code is the least important things. What is important is the functionality. So if I have to spend my time, I would like to spend my time on refining the functionality that my software has to deliver. Then the code is a necessary for implement that functionality. But what is relevant is the functionality, not the code. The code can be done automatically, so we can spend our time on the functionality. Once the software unit has been implemented and verified, we have to do the testing. The testing must demonstrate that the software unit fulfills the software unit design specification and do not contain undesired functionalities. So you must establish a test procedure and perform the test to fulfill this goal. So you must demonstrate that you tested the software and you have not any unintended functionality on your unit. So you have to demonstrate that your software is compliant with the specification, your software is consistent with the hardware-software interface, that you implemented the specified functionality, that you do not have unintended functionalities, that your software is robust, and you have enough resources for running your software. This is very complex. You cannot do this unless you have a structured approach. Indeed, we will have a lecture devoted to testing. So we have to understand how to do testing properly. Testing will be done using a requirement-based test. This means that we will analyze the requirements for the unit that we designed, and we will derive a test based on the requirement that is able to, let me say, activate adequately our unit so that we will have confidence that we tested well our unit. Then you will have also to do interface test. So you have to check whether the software is behaving correctly according to the specification of the interfaces with which the software has to interact with. We are expecting data over a certain protocol with a certain timing. Is our implementation of the unit correct? So are we consistent with the protocol or not? What happens if the interfaces are not following the the specified protocol? These are all things that we have to check. Then our item, our software, will contain mechanism to detect faults. So how do we check the behavior of that mechanism? This is something that we inserted in our code. We have to check whether, when we have faults, the behavior of the software is correct. And for this, we will do fault injection testing. Then our software will require some hardware to run. So we will need some memory, we will need some CPU time for doing that. Is the software consistent with the hardware that we will use? Do we need much more memory than what is actually available on the target? Do we need more computing power than what can be provided by the target? This is something that we have to do with resource usage test. And then, if we adopt a model-based design, so that we have an automatic generator of code, we have to check whether the code generator does not introduce unexpected behaviors. And so we will have to check whether the model is behaving consistently with the implementation. And this is back-to-back comparison between model and code. All the testing activities are meaningless if we do not have a metric to quantify the goodness of the test. So we do test, but how much do we test? We need to have a way for measuring the quality of the test. Do we test all the software? Is something that we haven't tested? How can we quantify that? We need to have metrics. The metrics that are suggested are the following. So we need to use statement coverage. So we must be able to count how many statements of our function are executed by our test. How many branches are covered by our test. And then we could also even have to provide a special metric that is called MCDC, Modified Condition Decision Coverage. Again, we will have a lecture devoted to this. We will enter in detail. For the moment, it is important that you understand the process. We test the software. We take measures to understand the quality of the test. If we have not obtained the full coverage according to the specified metrics, we have to test more. The test environment must be representative. So your item is going to be deployed in a vehicle. Your software is going to be provided with input stimuli that are coming from the vehicle. We must be able to test the software in an environment that is as close as possible to the actual environment where the software will be deployed. But this obviously is not possible. You are writing a function in a complex algorithm that is going to be deployed in an electronic control unit that is going to be inserted in an engine. And you have a team of 50 developers. You cannot imagine that each developer has its own engine. Do the test, too expensive. And you cannot imagine that each developer has to queue for accessing the single engine that is available in the factory. It will take too much time. So you need to find a way for providing the software developer with a working environment that resembles the actual environment. For this, we will do hardware in the loop testing. We will have environments that are intended for reproducing a reasonably accurate model of the environment where we will be deploying our software. Again, this is another important element of model-based design. With model-based design, we can model the environment. alongside the function we want to implement. And then we can simulate the function alongside with the model of the environment. And so we can test whether our function behaves correctly in an environment that is very close to the actual environment. Now we completed the design of the units. We have to glue together all the units. It is like you have a program made of 10 functions. You developed each function independently. You tested each function independently. Now you write the main of the program, where the different functions are called and communicates with each other. This is the software integration. You put together all the different functions that you have developed and tested independently. So when you put together the functions, you have to validate whether they stay together nicely. So you have to do the software integration testing. Here the goals are the same as before. So you have to verify whether you are compliant with the architecture that you specified, with the hardware software interface, with the specified functionalities, the robustness. So you have to check the absence of inaccessible software. So think about the case that we have seen the first or the second lecture about the Ariane failure. Are all the functions in our code invoked? If not, why? Is this because we haven't specified a good test, or is this because that function is not accessible in a normal, with an exhaustive test case? And if so, why do we specify that function? Why do we place that function in our code? And then you have to check whether you have enough resources for running the integrated software. Again, the methods are the one that we have seen before: requirement-based test, interface test, fault injection, resource usage, back-to-back comparison between model and code. The methods for deriving the test are the same. So we do analysis of requirements, generation of equivalent classes, the analysis of boundary values. We will see this in detail, so don't be scared. And then we have to provide metrics. So we test and we measure what we tested. This time we are not interested in the single statements, because the single statements are inside the functions that we already tested. We are testing the assembly of the different functions. So we have to check whether each function has been executed at least once, and this is the function coverage. And then we have to check whether each statement that calls a function has been executed at least once, and this is the call coverage. Again, we do test, we measure, we check the coverage. If it is not 100%, we improve the test. And again, the test environment must be as close as possible to the real environment. Once the test has been completed, so we are confident that what we integrated is what we specified, we have to do the verification of software safety requirement. So we have to demonstrate that the embedded software satisfies the requirements in the target environment. So just to make clear the difference. In unit testing and integration testing, we can do the activity on our PC. So we have a simulation model, for example. We do all the tests with the simulation. We generate the code. We compile the code on our PC, and we run the software. It is very close to what you have done in programming courses.
So you write a program, you test the program on the PC. Now, when verification of software safety requirements has to be addressed, you move into the target environment. So your software is not going to run on the PC, it's running on the real hardware or on a suitable model, physical model of the real hardware. And here you have to take into consideration the real-time aspects. When doing the simulation on the PC, when running the software on the PC, timing is not relevant because you cannot have the real hardware. So your PC is much more capable of the hardware that you have in your electronic control unit, where your software will be deployed. So all the activity that you do are basically not able to consider the time in which operation will take place in the real environment. Now we have to move towards the real environment because, for example, we have to verify whether we are able to react according to the fault interval reaction time that we specified. So we have to be able to do testing that is able to give us precise measurements of the time spent while running our software. For this, we have a number of techniques like hardware in the loop, electronic control unit, network environment, and vehicles. We will see this in detail when talking about software testing in detail. For the moment, it is important you get the concept. The concept here is not just to do yet another testing. This is a testing that looks into the performance aspect of your software in the real environment, okay? You specify that you must enter the safe state in 100 milliseconds since the detection of a fault. Here is where you can measure that. So you trigger a fault, and then you analyze how the software responds. You measure how long does it take to say, I am in the safe state, and then you verify whether that time is within the specified time. This is the type of activity that we are looking for here, okay? Last step is where you bring together the software that you wrote with the hardware that you designed. So it is here. So here you have to verify whether your software stays nicely on your hardware. Why you have to do that? Well, this is because the software and the hardware are independently developed. Once you write your software, the hardware can be still in design. So you don't have the chance of doing all the testing activity that are required during the software development phase on the real hardware, because you may not have it. Let's imagine that you want to enter the market with a new design that is using a new fantastic microcontroller that is not yet available. So you can start your software design, you can start your hardware design because you know the specification of the new microprocessor, but you don't have the capability of building a board that hosts that processor not before 1 year after the beginning of the project. This is because the silicon manufacturer is not able to ship you the chip. This is normal business. If you are thinking about the design of the next electronic control unit that has to be in the market in 2023, you know which is the roadmap of your silicon vendor. So you know which is the device that you can use in 2 years from now. You already have the specification. It is defined, you know the pinout, you know the functionality, but the chip is not available. So what do? You wait 2 years for having the real chip, you start the design of a PCB, takes 1 year, and then at the end of that you can start writing software. You will not meet the 2023 deadline. You will not be able to do that. So you need to do development concurrently, okay? And then you have to hope for the best, because the software is developed with some assumption. The hardware is developed concurrently, and then the two should stay together nicely, okay? So it's not easy at all, and software and hardware and software integration and testing is a very important activity. So you have to test the compliance with each safety requirements. You have to verify that the item implements the safety requirements. And this is done through a number of steps. We will not enter in detail of this. Let me just say that we will test at the hardware software level. So do they stay nicely together? We will test at the system level. When our electronic control unit with our custom hardware and custom software is deployed alongside the other electronic control units that are in the vehicle, do they stay together? Eventually, when we brought everything inside the real vehicle, is the real vehicle working correctly? And for this, the standard prescribes a number of steps. Just to give you a flavor of what we have to do here, when addressing hardware software level testing, we have to check whether the functional safety of the element works properly when the fault happens. Is the hardware and the software behaving correctly together? Then we have to check which is the performance. Is the item that we developed performing, as far as time is considered, consistently with what we are expecting? Are the interface working as they should? Does the element's functional safety mechanism works for all the faults that are relevant? Then is the item that we designed able to deal with any workload that can be provided to the item? These are the questions that we have to satisfy. Then the same question applies when we take our hardware and software and we insert in network with all the other electrical items we have to interact with. And this is the system level testing. And eventually we do vehicle level testing. So when we brought the item in the real vehicle and we start driving on the road, what is happening? Is everything working fine? These days, if you are lucky, you can find on the street of Torino some prototype of Levante, the SUV from Maserati. Well, they are doing vehicle level testing. So they are checking whether all the parts of the vehicle stays nicely together. And you can arrive to this point only after you have done all the previous steps, because you have to be confident that when you deploy something on the real vehicle, you put a driver in the vehicle and you make the car moving in the city when there are people around, you will not have risk, okay? This is the purpose of all these steps. Well, here I gave you a very quick view of the implementation phase. As I said, very quick view. This is a kind of synopsis for the topics that we will cover in detail in the next lectures. But although quick, I hope this gives you the global picture where we have to work with. Then there is a lot of material that you haven't understood here yet, because in order to understand this, we have to enter in detail. But again, this is a kind of summary of what is awaiting us from the next lecture. Okay? So, as I said, I have to close here, but before we leave, let me say that in the next week, we still have a lecture. It is on Wednesday. We will do exercise. It is still true what I said last time. Applying concept phase that is required at the exam is complex. You need to do exercises. So on Wednesday morning, we will do exercise together. Then we will have the Easter break. We meet again on Friday. On Friday, we will probably do, so Friday after Easter, we will do an exercise, and then we will address a new topic, okay? We can close here.